Okay, looking at the problem of the box and the truck bed, trying to look at it from the broadest perspective. In the road frame, and this is after the brakes have been hit, so I should probably say that. In the road frame, while braking, the net force is, and you have to draw free body diagrams and so forth. The box is going to have gravitational force down, it's going to have a normal force up, they're going to be in balance, and you're going to have the frictional force. Okay, the frictional force is the only thing that's not in balance. And we've said that the frictional force has magnitude 1/4 the weight of the box. Well, if big M is the mass of the box and big mg is the weight of the box, and 1/4 of that is the magnitude of your net force. If the positive direction is your direction of motion, that will be the I direction, then the frictional force is opposed to the direction of motion. And it'll be negative 1/4 mg times I. And that gives you, well, 1/4 of g is 2.45 meters per second squared. We got the negative and we got the m over here and we still got the I. So right there is an expression for your net force. Acceleration of the box is net force divided by the mass. Now, I was a little careless. I didn't put arrows over these things, which are being represented here as vectors. I didn't have the arrows here, but since they're vectors, they should have been represented with arrows over them. Okay, so we take the net force, divide by the mass, and of course the mass goes away and everything else is left, and here's our acceleration. Negative 2.45 meters per second times I. Now, that's true whether we're in the frame of the road or within the frame of the truck bed. Because within the frame of the truck bed, well, the forces are still what they were. Okay, the fact that the truck bed happens to be moving doesn't influence the forces experienced by the box. Okay, now if we choose t equals 0 when the brakes are first applied, as opposed to the instant the last ice age ended, which wouldn't be a good choice because that's ambiguous within plus or minus a couple thousand years. You have to first, it's not a well-defined instant in time because what's your criterion for the end of the ice age? Okay. Is it when the ice finally recedes from your front door? Just when is it? Okay, well, anyhow, t equals 0 and the brakes are first applied. Okay? And with that, we're going to be able to say that the velocity of the box as a function of t is then 8 meters per second, which was the velocity it initially had, minus the 2.45 meters per second squared times t. At t equals 0, that gives you 8 meters per second. And every subsequent time, it accounts for the acceleration. Same for the velocity of the truck bed. Except, of course, that the acceleration of the truck bed relative to the road is negative 4.4 meters per second squared. Okay? And from this, we can integrate, take antiderivatives to determine the position of the box and the position of the truck bed end. This is the position of the truck bed end there. I don't know if you can read that. Should have capitalized the B and the E. I can do that. Truck bed end, but I just do that with lowercase letters here, TBE down here. Okay? Well, if I integrate this, I get 8 meters per second times t, or this, minus half of this times t squared, because the antiderivative of t is t squared over 2, plus an integration constant. Then at t equals 0, the position is whatever the position of the box is at 0. Okay? And that's whatever it is relative to whatever point I'm using as my reference. It might be the position at which the ice age last ended, I don't know. But it's probably some position along the road. Okay, but relative to that position, we have the position of the box at time t equals 0. And that's the value of our integration constant, because x box of 0 has to be the position of the box at t equals 0. Similarly, we get a very similar expression for the truck bed, and same velocity, initial velocity. The acceleration being negative 4.4 meters per second squared, we're going to get negative 2.2 meters per second squared times t squared here. And of course, the initial position of the truck bed end is the initial position of the truck bed end. The t equals 0 position is this. Okay, so you should understand all of that. And the only things we don't know are this and this, but it's not going to matter exactly what this is or this, as long as they're measured from the same point. We know that this is 2.1 meters in front of this, because when the brakes are hit, the box is 2.1 meters from the end of the truck bed. Okay, so we're going to be able to use that. Now, the collision occurs when? When this is equal to this. When the truck bed end and the box are at the same position. That's when they strike, when they collide. So if these are equal, that means that this minus this has to be 0. Okay? So if I do the truck bed end minus the position of the box, the 8 meters per second times t goes away. So this subtracted from this still leaves us negative 1 meter per second squared times t squared. And we have truck bed end position, initial truck bed end position minus initial box position here. And then we rearrange that, and we find that 1 meter per second squared times t squared is equal to the difference between the initial position of the box and the initial position of the truck bed, which is the 2.1 meters given in the problem. And now we easily solve for t. And from that, then, we can evaluate the velocity of the box and the velocity of the truck bed end at that instant and see what the difference is and see how hard the box hits the truck bed end. It's going to turn out that we didn't really need to do all this, but it was worth doing, so we can see why we might want to use energy conservation in order to analyze the situation. In the truck bed frame, everything is the same except for this 8 meters per second. In the truck bed frame, the velocity of the truck bed is 0, the initial velocity of the box is 0. So we don't have the 8 meters per second anywhere, and these will be our positions. Okay? Now, we just still subtract this from this and solve for t, and we'll still get the same time at which the box collides with the truck bed end. We'll be able to plug that time in here and get the difference in the two velocities, so then we'll know what the velocity of the box is relative to the end of the truck bed, and that's how it'll tell us how hard the box or how fast the box is going relative to that end. How hard does it hit? Okay, now we can do the same thing with the work kinetic energy theorem, or the work energy theorem more generally, and we'll do that in the next video.